In the next few videos, we're going to look at how we can use Ampere Circuit Law in order to get an expression for our magnetic field intensity due to some current distribution. So what we're going to see is that this is very similar to what we did with Gauss's law when we were talking about charge distributions. So when we're using Ampere Circuit Law, the first thing that we want to do is to create something called an Imperium Path. And so of course, as you might recognize, this is similar to a Gaussian surface. And so along this Imperium path, we want our magnetic field H to be constant. And so the reason is we want to be able to pull that H expression out of our integral. So we're thinking about that integral form we saw in the previous video. So remember we said our current enclosed is equal to the integral around some closed path L of H dot dl. And so if our H is constant along that path, of course, we can say this is H in some vector direction, and then we can just pull the H out front of the integral. Okay, so let's take a look at some of our previous configurations and see if we can't determine the same H value that we saw before. So let's start with this infinite line current. And so I've got some current that is flowing along our z-axis, and so let me put a direction. Not that it's really going to affect us too much, it's just going to change the vector direction. But let's say that this current is flowing upwards. And so I'm interested in finding the magnetic field intensity at some point P. And so in this case, our Imperium path is going to be a circle because on that Imperium path, we're going to have the same magnetic field intensity. So my Imperium path is a circle containing point P. So I'm going to try my best to draw this accurately, but as always, you're probably going to have to sort of use your imagination a little bit here. So we've got this circle that is coming around, and so that should be equidistant from our axis. I've drawn it skewed a little to the right, it looks like. And of course, for clarity, let's sort of just cover that up because in the backside, that's sort of going around behind that infinite filament. Okay, so that is our Imperium path. So we notice it's going through our point P. We also need to specify a direction. So let's say that along our Imperium path, we're going in this direction. So then we can talk about some differential length on that Imperium path. So let's say we look at some small portion here. And so of course, we're still going in this direction. And so that's going to be our dl. So in this case, because we are going in a circle, and due to how we have this oriented with our x, y, and z axis, so in our coordinate planes here, we can use our cylindrical coordinates to best represent this, or most easily represent this. So first, let's say that our point P is some perpendicular distance away from our filament rho. And so what we can do then is we can say our dl is just going to be rho d phi in our phi direction. And so you could go back to our handout for differential surfaces and differential lengths and volumes in order to sort of recall that if you have any issues remembering that. So now that we have that dl expression, we're going to come back to this general equation up here, which was our integral form of that Maxwell's third equation. And we're going to say we have some current enclosed, which is just a general I, and so I didn't label that, but let me come back up here briefly and just say this is some current I, so we're going to keep it general. So our current enclosed in that circle is of course I, and now we have the integral along the path L, and so of course it's a closed path, which is H in our phi direction times our phi unit vector. And the reason we're doing this is we know from right hand rule we put our thumb in the direction of I, and we know that our H is only going to be along that phi direction from where our fingers on the right hand are curling. So we're dotting that with our dl, which we said above is rho d phi in our phi direction. And so again, because this h phi is constant along L, so this is constant along L by design, and the reason is because anywhere along the circle we're the same distance rho away, so we can pull that out front of the integral, so we can say we have h phi out front, and now we have the integral along some closed path L, and of course u phi dot u phi is just going to be 1, so we're left with the integral of rho d phi. Now the limit for our path L is going to be phi going from 0 to 2 pi, so of course we're completing a full circle. And so what we get then is that that current enclosed is just equal to our h phi times integrating from 0 to 2 pi of d phi is just going to give us 2 pi, and then we still have that rho along as well. And so of course now we can solve that for our h. So we can say that our h in general is only in the phi direction. So I'm going to sort of put a u phi at the end. And so we have I divided by 2 pi rho, where again rho is the perpendicular distance from that filament. And this is going to be in the phi direction. And so what we'll notice is that this is the same expression that we found earlier. So same as before, which of course we would expect. It'd be very problematic if two different methods give us two different expressions. But this is the exact same expression we had for an infinite filament before. And we arrived at it a lot easier than how before we considered some finite filament and then we extended it to our special case to get our infinite filament equation.